Hello, welcome to another module in this massive open online course. So, today let us discuss a new concept. This is the null space of a matrix. This is what we call as the null space of a matrix, which is defined for a matrix. What is the concept of a null space? Consider a matrix A, which is of size m cross n, then the null space of this matrix, which is denoted by n of A, null space. So, this is your null space of A, that is the set of all vectors x bar such that A x bar equals 0, that is the null space, that is the set of all vectors x bar such that A x bar equals 0. Okay. Now, the null space, remember that the terminology is justified because the null space is in fact it is a subspace, right. So, the null space is a subspace. What do we mean by a subspace? That is, if we consider any two vectors x1 bar comma x2 bar belonging to the null space, then their linear combination alpha x1 bar plus beta x2 bar also belongs to the null space. This is not very difficult to see. For instance, let us take for instance x1 bar belongs to the null space. This is easy to see because x1 bar belongs to the null space. This implies that Ax1 bar equals 0. Similarly, x2 bar belongs to the null space, Ax2 bar equal to 0, since Ax2 bar belongs to the null space. Now, A times alpha x1 bar plus beta x2 bar, naturally it is not very difficult to see, this equals alpha times Ax1 bar plus beta times Ax2 bar, each of which is 0, X1 bar is 0, X2 bar is 0, this is 0, which implies that also by definition alpha x1 bar plus beta x2 bar equals 0. That is why it makes it a subspace. Remember, what is a subspace? Subspace is nothing but whenever two vectors belong to the subspace, their linear combination also must belong to the subspace. We call that such a set, basically a subspace, right. So, the null space of a matrix A is in fact a subspace, right. Now, the interesting that you observe over here is that 0 always belongs to the null space of any vector. So, 0 always belongs to the null space, right, of any matrix. That is easy to see because A into 0, this is equal to 0. Now, if there is any other vector x bar such that x bar not equal to 0, but Ax bar equal to 0, then we call it a non-trivial null space. Then it is frequently known as a non-trivial means non-obvious, right, because 0 is belongs to the null space of any matrix, right. So, it's also, so if you have 0, then basically it's basically simply known as the trivial null space. Now, if there are other vectors, if there is even a single vector in the null space other than the 0 vector, then it is known as a non-trivial null space. Now, obviously the null space cannot contain, if there is it's a non-trivial null space, then it cannot contain a single vector, because if x bar belongs to the null space, then alpha times x bar also belongs to null space. So, it either contains it's either the trivial null space, that is 0, which contains only a single element. The non-trivial null space always contains an infinite number of vectors, all right. Okay. Other interesting result, for a square matrix A, if the null space is non-trivial, if the null space is non-trivial, then A is not invertible. If a square matrix is a non-trivial null space, that is, it is easy to see. For instance, if there exists Ax bar equal to 0, that is, x bar, consider x bar not equal to 0, but Ax bar equal to 0. Now, if A inverse exists, then we must have, multiplying both sides by A inverse, we must have A inverse A into x bar equals A inverse 0 equal to 0, which implies A inverse A is identity, so which implies x bar equal to 0. But we started with the assumption x bar is not equal to 0. So, if you go back and look at the assumption x bar is not equal to 0, we are able to show. So, this is basically a contradiction. Therefore, x bar is not equal to 0, this implies A inverse does not exist. Where is the contradiction arising? Because we are assuming A inverse exists, this implies A inverse does not exist, this implies A naught, this implies A not invertible. Okay. So, if a square matrix has a non-trivial null space, that is, there is an x bar which is not 0, but Ax bar equal to 0, then the square matrix is not invertible, all right. Okay. The other condition for singularity, that is, A is non-invertible or A is basically singular. The other condition we saw is basically determinant. So, these are all equivalent conditions, that is, if the and we can show that if the determinant is 0, then basically there also exists a non-trivial subspace. So, all these are, another way to say that is a singular matrix is that if it is an n cross n square matrix, then the rank of A is strictly less than n, right, it is a rank deficient. So, all these are equivalent ways of how equivalent, you can say there is an equivalence between all these things, these different properties of basically a singular matrix. Okay. All right. Now, let us look at a simple example to determine the null space. Consider A equals the matrix 1 1 1 1, A equals 1 1 1 1 1, 1 2 3 4 5. Now, we want to determine n of A, or rather determine a basis determine a basis for NI, right. So, any vector that belongs to the null space we must have times x1, x2, x3, x4, x5 must equal to 0. Therefore, now let us expand the first condition. This implies that x1 plus x2 plus x3 plus x4 plus xy equal to 0. This basically implies that let us first start with the row reduced form, then it becomes more convenient. Now, do row operations. Let us perform row operations. First, let us replace R2 by R2 minus R1. Then we have the matrix equivalently becomes, right, the matrix equivalently becomes 1 1 1 1 1 0 1 2 3 4. Now, let us do another row operation. Let us do R1 replaced by R1 minus R2. Now, the matrix becomes 1 0 1, I am sorry, 1 0 minus 1 minus 2 minus 3 0 1, this stays as it is. Now, we are in business. Now, let us find the null space of this row reduced matrix. So, of course, you can see there are 2 pivots. So, basically the rank is 2, that is not very difficult to see. Now, let us determine the null space. So, we have 1 0 minus 1 minus 2 minus 3 0 1 2 3 4, this matrix times x1 x2 x3 x4 x5, this is equal to 0. This implies, now let us expand the conditions, x1 minus x3 minus 2 x4 minus 3 x5 equal to 0. This implies x1 equals x3 plus 2 x4 plus 3 x5. Let us write the second condition from the second row. Now, this implies that we must have x2 plus 2 x3 plus 3 x4 plus 4 x5 must be equal to 0, which implies x2 equals minus 2 x3 minus 3 x4 minus 4 x5. Therefore, the element x bar is of the form, that is any x bar belonging to the null space of A is of the form, you have the free ones x3, x4, x5, and then you have x2 which is minus 2 x3 minus 3 x4 minus 4 x5, and then you have x3 x1, which is basically, if you look at this, x1 equals x3 plus 2 x4 plus 3 x5 and now you can also write it interestingly. You can expand this as, it is not very difficult to see, you can expand this as x3 times 1 minus 2 1 0 0 plus x4 times 2 minus 3 0 1 0 plus x5 times 3 minus 4 0 0 1. So, it is a linear combination. So, any element of the null space is a linear combination of these 3 vectors, right. So, any vector x bar, now you can see very interestingly your x3, x4, x5, these are the free variables, and any vector belonging to null space can be expressed as a linear combination, that x1 times the first vector, I mean x3 times the first vector plus x4 times the second vector plus x5 times the third vector, right. So, basically these vectors form a basis for the null space of A, right. So, any vector, so these vectors since any x bar belonging to null space can be expressed as a linear combination of these 3 vectors. Right. So, these form a basis, and you can see being a basis they themselves are, that is each of these also belongs naturally, they form a basis. So, they also belong to the null space of A. You can quickly check that. For instance, if you consider the vector 2 minus 3 0 1 0, multiply that by our matrix 1 1 1 1 1 1 2 3 4 5, and what you see is you get 2 minus 3 minus 1 plus 1 0, 2 minus 6 plus 4, that is also 0. So, this indeed belongs to the null space of A, and similarly you can check for the other vectors. Similarly, this is an exercise for you. Similarly, what you see very interestingly is the number of elements in the basis, that is the rank, that is the basis is of dimension, number of basis vectors. So, you can see from here number of basis vectors equal to 3, implies dimension of n of A equal to 3. Now, this dimension of n of A, this is also termed as the nullity, right. This is also termed as the nullity of the matrix. And now, you can also see, which in this case equal to 3, for a nullity of A equal to 3, right, and nullity because the number of elements in the base is equal to 3. So, nullity of A is equal to 3, and if you can look at this, now you go all the way back and you look at the rank of A, it is not very difficult to see, you have 2 pivots, right. So, you have 2 pivots. Rank of A equal to 2, and therefore, you have rank the famous rank plus nullity theorem. So, you have rank plus nullity which is equal to 2 plus 3 which is equal to 5, which is essentially equal to n, that is number of columns of A. So, rank plus nullity equals the number of columns of rank plus nullity equal to n. This is your famous rank theorem, or this is a famous rank nullity property, right. Rank nullity property is a very interesting. There is a dimension of the rank plus the dimension of the null space must equal the number of columns of the matrix A. Okay. Let us look at an application of the null space. The null space is again another very interesting concept which has several applications. So, applications of the null space. Now, an interesting application is in circuits. Consider the simple circuit below. I am going to draw it as simply a set of so these are nodes 1, 2, 3 and 4. I am going to draw another edge. So, we are going to call this as the currents as I1, 2 to 4 as I2, 4 to 3 as I3, 3 to 1 as I4 and 3 to 2 as I5. Now, let us define for this circuit what is known as the adjacency matrix. What do we mean by the adjacency matrix? You have A is of size m cross n, this is the adjacency matrix. What is m? M equals basically the number of currents or the number of edges, the number of edges in the circuit. What is n? N equals the number of nodes. N equals the number of nodes. Therefore, now in this graph we have 5 edges, right. This is, you have 5 edges, which means m equal to 5 and n equal to 4 nodes. So, A is of size 5 cross 4. Now, what is the property of A? How do we construct A? We have Aij equal to 1, Aij equal to minus 1, no, Aij equal to minus 1 if current I leaves node j, Aij equal to plus 1 if current I enters node j, else if the current I neither leaves node j or enters node j, it is equal to 0, right. So, Aij equal to minus 1 if the current I leaves node j, it is equal to plus 1 if the current I enters the node j, and if there is neither is happening, the current I neither leaves node j or nor enters node ij, neither enters node j, then Aij equals 0. Let us construct the adjacency matrix for this circuit, alright, that will illustrate this. Again, let us go back, let us take a look at this circuit. A equals, we already said this is a 5 cross 4 matrix, 1, 2, 3, 4, 5, 1 for each. So, 1 row for each current and 1 column for each node. So, this is a 5 cross 4. So, these are basically your currents and these are basically your nodes of the circuit. Now, look at this, current I1 leaves node 1, enters node 2. So, this is minus 1, leaves node 1, so minus 1, enters node 2, so plus 1, and the rest are 0. Current 2 leaves node 2, so minus 1 for second column, and enters node 4, so plus 1 for fourth column, rest of the entries are 0. Current 3 leaves node 4, enters node 3, leaves node 4, so minus 1, enters node 3, so plus 1 for node 3 and 0 0. Current 4 leaves node 3, minus 1, enters node 1, so plus 1 for first column, 0 0, and current 5 finally leaves node 3, so minus 1, and enters node 2, so 1 for second column, rest are 0. So, this is the adjacency matrix. This is basically your adjacency. Previously we have seen the vertex matrix, this is basically different, this is the adjacency matrix, right. So, minus 1 1 1 0 minus 1. Let me just do a quick check, it is always a good idea to check. All right. So, that is now what is, now observe the current vector, consider the current vector. Now, consider any current vector I bar equals I 1, I 2, I 3, I 4, I 5. Then the property of the null space says that I bar belongs to the null space of A transpose, where A is the adjacency matrix, right. So, this is the, remember, this is the adjacency matrix for this circuit. So, any current vector of the circuit, any legitimate current vector of the circuit must belong to the null space of A transpose. Let us verify that. We have once again A equal to minus 1 1 0 0 0 minus 1 0 1 0 0 1 minus 1 0 0 1 minus 1 1 0 minus 1 0 0 minus 1 0 0 1 minus 1 0. Now, A transpose, let us look at what is A transpose. A transpose equals minus 1 0 0 1 0 minus 1 0 0 1 0 1 minus 1 0 0 1 0 0 1 minus 1 minus 1, and finally 0 1 minus 1 0 0 1 minus 1 0 0. Now, this is the null space of A transpose. Now, let us write this, verify the current vector. Let us multiply this by the current vector I 1, I 2, I 3, I 4, I 5. This is equal to 0. This implies, what does this imply? If you look at this, minus I 1 plus I 4 equal to 0. This implies I 4 equal to I 1. But if you look at this, think about this, all this is saying is basically, if you go back and look at this circuit, I 4 equal to I 1, that is current entering, I 4 is current entering node 1, I 1 is current leaving node 1. So, current entering node 1 must be equal to current leaving node 1. So, this is the Kirchhoff's current law for the first node, that is the interesting point. So, what all this is saying is the Kirchhoff's current law, the KCL. So, I 4 equal to I 1, this implies current entering node 1 equals current leaving node 1. This is nothing but the Kirchhoff's current law. Or KCL. for node 1. That is essentially what this is, right. So, this is the Kirchhoff's current law for node 1. Similarly, if you look at the second one, that says I1 minus I2 plus I5. So, the second row says, so this is basically the first row. Now, the second row, let us write it separately over here. The second row will be I2 minus I am sorry I1 minus I2 plus I5 equal to 0, which implies I1 plus I5 equal to I2, I1 plus I5 equal to I2, which is nothing but current entering the node 2 is equal to, so I1 plus I5 equal to I2, I1 plus I5 equal to I2, let us look at that. I1 plus I5 equal to I2, current I1 plus I5 is current entering node 2. So, the left side is current entering node 2. And I2 is basically current leaving, current entering node 2, current leaving node 2. This must be equal. This is basically KCL for node 2. This is basically your KCL for node 2. Similarly, if you expand the third row, you will get I3 equal to I4 plus I5, third row. I3 equal to I4 plus I5, let us check if that correct. I3 equal to I4 plus I5, I3 exactly current entering node 3. Current leaving node 3, and finally you have I2 equal to I3, fourth row, expand the fourth row of A transpose. What do you have? Fourth row, if you expand, you get I2 equal to I3. Current entering node 2, I am sorry, current entering node 4, I2 equal to current entering node 4, I3 equals current leaving node 4. That is it. So, this is the KCL for node 3. And this is your KCL for node 3, and you have the KCL for node 4. That is essentially what you have. So, if you write the adjacency matrix of the graph, right, if you write the adjacency matrix for the circuit, the current vector, any legitimate current vector, because it has to satisfy the KCL equations for every node, this has to belong to the null space of A transpose, and these set of equations translates to nothing but the KCL or the Kirchhoff's current law at every node. So, that is a very interesting property, and the null space in general has many applications. As I already seen, we already shown null space, if the matrix has a if a square matrix is a non-trivial null space, then it shows that the matrix is basically not invertible, it is a singular matrix, alright. So, it is a very important property of a matrix. So, let us stop our discussion here and continue in the subsequent modules. Thank you very much.